I didn't say that. Let me begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for the break just completed, and just ask you to guide our steps today. Help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. So, yes. So we're now doing double integration over general regions. So let's get into it. So last time we just did double integration and triple integration over, you might say, box-like regions that have constant bounds. But now we're going to take it up a notch, so to speak, and talk about type 1 and type 2 regions. So a type 1 region, it has the form x comma y such that a less than or equal to x less than or equal to b, and g1 of x less than or equal to y less than or equal to g2 of x. Right? In other words, a type 1 region is one for which you can graph it something like this. Here's A, here's B. There's a clearly defined bottom, there's a clearly defined top, something like this. Right? So, in short, if you draw a little vertical rectangle in here, you can always sort of fit that in. And if you take a particular point in there, x comma y, you have, on the one hand, a less than or equal to x less than or equal to b, but you also have that g1 of x is less than or equal to y is less than or equal to g2 of x. All right, so like the graph on the top, I'm calling g2. The graph on the bottom is g1. So that's a type 1 region. Now type 2 region, same kind of story, but here we have x comma y such that c is less than or equal to y is less than or equal to d, and h1 of y is less than or equal to x is less than or equal to h2 of y. All right. And so for a type 2, this type 2 region, so let's put it into words. A type 1 region has a clearly defined top and bottom, right? And the sides are just x equals a and x equals b. But for a type 2 region, we have a clearly defined top and bottom, and the sides can be kind of wonky. So I'll make this one a little bit bigger. Here's x, here's y. So we're going between, let's say, B and C. And in this situation, we've got all right, so like this right here would be x is equal to h1 of y, and this guy over here would be x is equal to h2 of y, right? Now, as a practical matter, I sometimes call this, aw man, you're dead. I sometimes call this the top. This is the base. And this is the right x. And this is the left x, and if that's the situation, right? So, like I might use the label x. If I draw the typical approximating rectangle here, it looks more like this, right? And here, like the little bit of area there would be the right x minus the left x times dy, right? Whereas up here, if I was to talk about the infinitesimal area of that strip, I would have had the top y minus the bottom y, base, let's make it based here, base times dx, right? That would be the situation. Now, these things you've thought about before because you've calculated area bounded by curves, right? But what's new here is we're going to take these and we're going to use these as a framework for setting up a double integral. So we're not just calculating, area. We're calculating perhaps the volume, the signed volume under a graph, or something like that. Now, anyway, here's the theorem. Which is this, given R1 and R2 as in the definition on the other board, the double integral over R1 of f dA is equal to the integral from a to b, the integral from g1 of x to g2 of x, f of x comma y dy dx. And I'll put the parentheses in here for the moment, but of course, as time goes on, we sometimes omit these parentheses. But we are doing the inside integral first, and then the outside integral. But the new thing here, with respect to like last class, we didn't do this last class, is that now the integrals are not constant, like the bounds are varying, right? So now, so that's how that goes. On the other hand, the integral of a function over the R2 region, the way we would set that up is the integral from c to d, and then the integral from, say, h1 of y to h2 of y, f of x comma y, dx, then dy. All right? Any questions? I mean, I got a bunch of examples to show you, but before I do that, maybe I should try to derive these formulas for you. All right? Yeah.
How do you tell, does it matter which one's H1 and H2? Like, how do you tell if you're given
Yeah, it matters.
a function?
It'll take us about 10 examples to fully understand how it matters, but yeah. That is a totally reasonable question. So let me try to explain the top formula like geometrically. So I will attempt a picture. It may or may not work. We'll see how it goes. So we're going from A to B, right? And basically, I've got these sort of guidelines here. I've already messed it up. Oh, well, I'm going to stick with it. And then in between those, I've got an x naught, all right? Okay. Now, I'm supposing I'm looking at a type 1 region. I'm visualizing the type 1 region as a subset of the xy plane, all right? So, like, I can make maybe this one y equals to g1 of x here, and then over here somewhere y equals to g2 of x, all right? And so, not pictured yet is f. So I'm just talking about, like, the region that I'm integrating over is a type 1 region, and I'm identifying it for the sake of this graph with a particular subset of the xy plane, right? So like in my picture, I drew this like approximating rectangle. The approximating rectangle would be sort of like here in this picture. All right? So a typical point right here, x naught comma y, would have what? we would have a less than or equal to x naught less than or equal to b, and that y is sandwiched somewhere between, yeah, g1 and g2. All right. Now, as we're calculating the integral, so my goal is to derive. I'm trying to derive formula number 1 here at the moment. I'm going to assume that f of x comma y is greater than or equal to 0 for graphical simplicity. Yep.
The inequality should be y naught, or is it?
No, this is an arbitrary y. Can go anywhere between those. I have to think about an infinite family of those ranging from g1 of x. But that should be, however, this should be x naught. Was that what you're asking me? Sure? Okay. So, look, I'm trying to find, I don't want to draw the whole graph because it'll make my picture too muddy, but like, we're looking at z equals f of x, y, right? It's up here somewhere. And we're trying to find the volume under z of x, y, bounded by, you know, this, well, I don't want to shade it because then everything gets to be a mess, but, you know, the region is in here, right? Okay, so let me just picture one slice. Just one slice of it, yeah? So this is a slice, right? I tried. And so I don't know what the graph looks like. I mean, it could do all kinds of funny stuff up here, right?
That graph is your f of x, y.
Right, up here, we're looking at z equals to f of, well, apparently x naught, comma y, right? Because x naught, we're fixed in the particular slice here at x equals x naught. And so this slice here, right, has some particular area that I can say area as a function of x naught. What is that area? It's going to be an integral, right? It's integrating, we have to integrate,
From g of x naught.
yeah, g1 of x naught to g2 of x naught. The height is given by f of x naught comma y, and the thickness, I mean, I'm thinking about this kind of approximating rectangle at the moment, right? So the thickness is dx, and the height is like that. So that gives me the area of the slice. What's the volume of the slice? What's the infinitesimal volume of the slice? Well, the infinitesimal volume of the slice is simply a of x naught times the thickness of the slice, which is what? I said dx here. That's junk, right? That was supposed to be what? That's obviously a y, right? That's dx. So I take a of x naught times dx. That gets me the volume of that particular slice, right? And then I take the continuous sum to find the whole volume, right? So this tells me then that the total volume is the integral from a to b of, well, the integral of a of, you know, this one. Now I replace my x naught with x. So I've got g1 of x, g2 of x. I mean, I could write a dx naught if you'd like, but okay, so g1 of x to g2 of x, f of x comma y, dy dx, and there you go. That's the theorem. So the theorem is a straightforward application of the infinitesimal method that hopefully you've already seen, like in the previous class, you know. And to derive formula 2, it would be a similar picture, but we'd slice the loaf like the other way, right? Yeah. So, all right, let's do an example then. Now that we got this handy dandy formula. So example 1. And I don't have this picture in the notes, sadly, but oh well, there it is now. So I discuss what I go through what I just talked through here without a picture on page 271. I really should add a picture there. I guess I'm lazy. All right, so here is the region I'm going to look at. X comma y such that 0 less than or equal to x less than or equal to 1. 0 less than or equal to y less than or equal to x. All right, and I want to calculate the integral of e to the x squared dA. Let's see if we can do it. So here's how we go. This is quite clearly a type 1. So what I'm going to do is it's made to order pretty much, right? I integrate x from 0 to 1. I'm going to integrate y from 0 to x. And then I've got e to the x squared dy dx. All right. Now the good news is that we had to do the y integral first. What's the antiderivative of e to the x squared with respect to y? Y e to the x squared. All right. There has been some, we've reached a consensus. So y e to the x squared, very good. And that has to be evaluated from y equals 0 to y equals x, right? This is what the theorem tells us to do, is to do the inside integral first. I mean, that's the meaning of the notation, honestly. The theorem already happened in the first line. Now what? Integral from 0 to 1 of apparently x e to the x squared. When we evaluate 0, we get nothing. Well, this is better. We actually know how to integrate e to the x times e to the x squared, right? It's just a simple u substitution. So that's 1/2 e to the x squared, evaluated from 0 to 1. So the answer is 1/2 e to the 1 minus 1, or e minus 1 if you like. That's the volume of what?
The curve down yeah, 0 to 1, 0 to x.
Yeah, I mean, so it's somewhat irrelevant to, I mean, we can ask this question independent of your question, right? But the region 0 to 1, y equals x. So here's the region, right? It's like a triangle, right? We can visualize it that way. And the z equals to e to the x squared. When x is equal to 0, we get z equals to 1, right? So, but that's just here, right? And when x equals to 1, we get z equals to e. So that's about up here. So it kind of like goes up like this. So I don't know, I can't draw this. I mean, it's awkward to draw. So something like this is the graph, right? And we're basically finding the volume of this thingy, sort of like pizza shaped with a weird top, an exponential squared top, whatever that is. But yeah, that's the volume of that region. Or you could say it's the mass of a piece of pizza. There, the density, the mass per unit area is given by e to the x squared. Take the pizza. Or you could say it's the total charge that's carried on this pizza-shaped wedge if the charge density is given by e to the x squared. Like there's many interpretations. All right, here's another problem though. My focus today is not on interpretation, but rather calculation. So example 2, see if you guys can do this one. The integral from 0 to 1, the integral from y to 1, e to the x squared, dx dy. Now what's the problem here? So you asked me like, when do we need to use these theorems and stuff? Well, the answer is now, right? Because I can't do the inside integral. Because I don't know how to integrate e to the x squared. So I need to flip the order of the bounds, right? In order to do that, I need to draw a picture. I need to understand what I'm looking at. So here I have 0 less than or equal to x, less than or equal to 1, right? Oh, my bad. Not x, but what? Y. And I have y less than or equal to x, less than or equal to 1. So to graph that, our y goes between 0 and 1, right? My x is, here's the, the right x, and the left x is over here, right? X equals to y. So xl equals to y. And so my typical point is in here. So this is the region we're up against. So this region we could either write as a type 1 or a type 2, right? So like the integral as it's set up kind of gives you a type 2 description, but what's the type 1 description? Translating. Look, we have everything is between x equals to 0, right? And x equals to 1. So I have 0 less than or equal to x less than or equal to 1. And if I look at this here, right, I have 0 less than or equal to y less than or equal to x. So apparently, I can rewrite this as the integral from 0 to 1. It's just a quirk of this particular region that x ranges from 0 to 1 and y ranges from 0 to 1. But you notice now that we've got integral from 0 to x of e to the x squared dy dx. Oh, by the way, we're back to example 1 now. Yes. So if I want to ask example 1 in an unfriendly way, I don't ask it as I asked it. I asked it in this form. I say calculate this integral. And if you understand how to switch from type 1 to type 2, then you can do this, right? But understanding how to switch from type 1 to type 2 is a part of this course. Like that's the thing you need to learn if you don't understand yet. And it's not calculus, it's pre-calculus, right? It's just graphing. But it's nevertheless, well, we know what this works out to, right? We just did it. 1/2 what? E minus 1, right? By example 1. All right. Let's see if I can find you guys another example. I will introduce a new thing. It's the average of a function of 2 variables. What should the average of a function of 2 variables over some region be equal to? Do you guys remember how average worked in Calculus 1? What's that? Okay, well, here was the deal. 1 over b minus a, integral from a to b, f of x dx gave average of f on AB, right? So now what we'll do is average 1 over the area of R, integral over R of FDA. This gives average of f on R. So there you go. That's your definition of average. So I'll use that possibly to, I'll try to make some examples. Well, we'll see if they're easy, they're interesting or not. Let's find out. But so example 3, let's find average for f of x comma y equals to x times y over, we'll make R relatively simple here. This is kind of a throwback to last class, but just 0, 1 squared, right? So that's just a fancy notation for the unit square, right? So f average would be equal to, 1 over, so this notation is just meaning x comma y such that 0 less than or equal to x comma y less than or equal to 1. All right? Both x and y are taken from the unit interval. What's the area of the unit, the unit square? Just 1. So the 1 over 1 is kind of dumb. But then we got integrate from 0 to 1, integrate from 0 to 1 of xy. Now you guys tell me which comes first, dx or dy?
The area of 1.
It's a square with length 1 and width 1. Okay. So dx or dy, which come first? What do you think? It doesn't matter is the right answer. The answer is yes. Okay, so dx dy. All right, so let's do it. We've got integrate from 0 to 1. I'm doing the x integral first, so I have 1/2 x squared y. Evaluate that from 0 to 1. Still got my y integral after that. And so I've got the integral from 0 to 1 of 1/2 y, apparently, dy, which is 1/4 y squared, evaluated from 0 to 1, which is 1/4. So we get the average is a quarter for this function. All right. Now I want to do something a little bit harder. I want to calculate the average over a quarter circle. So this one's going to take us a little bit more work. I'll call it S, the quarter circle. And so what that's going to be is x comma y such that x squared plus y squared is less than or equal to 1, and x and y are greater than or equal to 0. Now we need a description of S that's like the thing I just erased, right? Can we draw a picture? So, like this, right? So I'm telling you x is non-negative, y is non-negative. So that puts us up in here, right? This is S. So so the outer thing is the unit circle, right? This point is what? 1, 0. This point up here, 0, 1, right? So here's the deal. I need to pick an arbitrary point in this set, right? And I need to either describe it in a type 1 or a type 2 fashion. I think type 1 is most natural, personally. If I can do type 1, I do type 1. Yep.
Does it matter where the point is?
It has to be an arbitrary point.
So it just has to be in that shape.
Yeah, we're trying to describe the inequalities which bound that point, but it has to be an arbitrary point, otherwise their inequalities are, you know, half-baked, I guess. So quite clearly, we can put 0 less than or equal to x less than or equal to 1 in that shape, right? Agree? And this down here, right, is y equals to 0. This guy up here is y is equal to the square root of 1 minus x squared. So I have 0 less than or equal to y less than or equal to the square root of 1 minus x squared. So that's my type 1 description of S. So, and we'll work it out before too long. What's the area of S? Yeah. Yeah, 1/4 pi. So pi r squared would be the whole circle, but the radius is 1. It's a quarter of that, so pi over 4, right? Now, we could work that out, but I don't want to distract us from that. We'll have much better tools to calculate the area of a circle here once we introduce polar integration, but we're not there yet. So let's just quote that from previous work. So the average then is 1 over, so it's, let's see here, 1 over pi over 4. And then we're integrating apparently from 0 to 1. And from 0 to the square root of 1 minus x squared. And then we got ourselves our x, y, dy, dx. So let's do it. So I've got a 4 over pi, integrate from 0 to 1. Now I'm integrating with respect to y, right? So I've got 1/2 x y squared evaluated from 0 up here to the square root of 1 minus x squared. Well, this is very good news because that means that that square obliterates the square root upon evaluation, and that just leaves us with 4 over pi, integrate from 0 to 1, of 1/2 x times, well, 1 minus x squared.
Could you still take the 1/2 out?
Take the 1/2 out. I mean, if you want to, sure. And then that is, I'll do it for you, 2 over pi, integrating from 0 to 1 of x minus x cubed dx, which gives me 2 over pi times 1/2 minus 1/4, which gives me 1 over 2 pi. I think, because that gives me 1/2 minus 1/4 is a quarter, and 2 over 4 is 1/2. So yeah, 1 over 2 pi. So in example 3, our region looks like this, right? In example 4, our region was that quarter circle. We found that the average on the square is larger than the average on the quarter circle. Does that make sense? I think it does, right? Because the square includes this part up here, right? All this stuff up here, and like xy is bigger up there, right? So of course that's going to make the average larger on the square versus the quarter disk. Anyway, I just want to show you this example. So Any questions? See if I can find another nice example. Well, I have a stupid number of examples in this section, like literally stupid number. Try to find another one that's got some niceness to it. Well, that one's nice, but that one's just square. All right, fine. What's it? Let us take a stab at this one. This is my example 6.212. All right. Example 5. Here we are faced with the integral from 0 to 1/16, the integral from y to the quarter power all the way up to 1/2 cosine of 16 pi x to the power 5 dx dy. So what do you guys think? Yeah, I think clearly we cannot do the integral as it's stated, right? So it must be that if for this to be a reasonable problem, perhaps changing the order of integration will help us. So first of all, we need to read from this. What's this tell us about the region of integration? This is like the integral over some region of the cosine of 16 pi x to the 5th dA, right? The question is, what's the region? Well, it's x comma y such that what? And how about y?
0 is less than or equal to y.
Very good. All right. So right here, apparently, the left x is y to the 1/4 power, and the right x is 1/2. So this gives us that the 4th power of the left x is equal to y. And of course, well, we've got a half. Let's see here if we can graph this thing. So we're going between 0 and a 16th. Y equals x to the 4th is something like this, right? And all right, so we have, oh, my bad, but my labeling is going to get in the way here. So that's the left. That's the left x. And these meet. Well, I'm not sure if they meet or not. Let's see here. If I put 1/16 equals to x to the 4th, what's that give me? Plus or minus 1/2, right? So apparently it looks like this. Where we're going from 0 out to 1/2 for x. And like, let me draw a picture here. So the original estimates we could picture like this. That's a way of understanding this and that, right? We're drawing a vertical strip from y equals 0 all the way up to y equals 1/16, right? Where the left is governed by x is equal to the quarter power of y, and the right is governed by 1/2. So that's what we have here. Now we want to flip this over. We want to look at it as a type 1 if we can. And by the way, it's not always possible to take a region and flip it to the other type. These examples we've been looking at have been forgiving in that way. These examples, these regions we've been looking at could either be looked at as type 1 or type 2. But in general, the story is more complicated. You might have to break it up into cases. All right, anyway, so we have type 1 description, 0 less than or equal to x less than or equal to 1/2, and 0 less than or equal to y less than or equal to x to the power 4. Now all of a sudden this problem's not so bad. See, we integrate from 0 to 1/2 for my x. We integrate from 0 to x to the 4th for my y. And we've got cosine of 16 pi x to the 5th dy dx, which is the integral from 0 to 1/2 of, if you don't mind, I'm just going to write down what happens, which is when I do this inside integral, it gives me x to the 4th times the cosine of 16 pi x to the 5th dx. Now technically I skipped a step there, right? The step I skipped was writing cosine of 16 pi x to the 5th times y is the antiderivative, evaluating that over the bounds, right, from 0 to up to x to the 4th. But it gives you this. And then we make a u substitution. So I've got a, let's see here, think about u is 16 pi x to the 5th. So, you know, du is 80 pi x to the 4th dx, which gives me the integral, which rather gives me, let me get to the point here, 1 over 80 pi, let's see here, cosine integrates to sine, so sine of 16 pi x to the 5th, evaluated from 0 to 1/2. Which is going to give me (1 over 80 pi). No, sine differentiates to cosine, so it's fine. And that's sine of, 1/2 to the 5th power is 1 over 32. 16 over 32 is 1/2, so that's pi over 2. And then minus the sine of 0. So lo and behold, the answer is 1 over 80 pi. Any questions? So I've been focusing on the case that you have to switch the bounds, because I think that is like the hard part here, and I think you guys should see it, right? I could just like relegate that to homework, but that's not how I roll. So example 6. Suppose we're integrating over the unit square. dA over 1 plus x squared times 1 plus y squared. Rather, let's say 1 plus y. Yeah, 1 plus y. So we're integrating from 0 to 1. Integrating, let me not, 0, this is not helpful. So let's do 0 to 1 Cartesian product with 2 to 3. So let's see here, I've got d y. So I want to show you guys a trick. Here's the trick. This integration over y, right? This integration over y has no x dependence. All right, this is important that it has no x dependence. The bounds don't depend on x, right? In that situation, I can factor this 1 over 1 plus x squared outside of the integration, and I can just do integral of dy over 1 plus y like that. But this is just a number, so I can just pull that outside the integral. And so in this particular context, something like this, where you have bounds which are rectangular, and your integrand is what I would call separable, it's a product of a function of x and a function of y, you can do this. This is a sneaky trick that makes life easier. See, because this is just inverse tangent of 1 minus inverse tangent of 0, the natural log of 1 plus 3 minus the natural log of 1 plus 2. And so the answer is just like pi over 4 times, the natural log of 4 minus the natural log of 3, right? Yep.
So you're saying whenever you can factor the denominator, or just whenever you factor in general, then you split
If
apart into
provided that the bounds don't depend on the variable. Like if I had an x dependence up here, I couldn't pull the 1 over 1 plus x squared out. But this is oftentimes the case that we have this pattern, and I'll use this trick as we go on. Yep.
Unless you ask us to calculate the exact amount, would that be simplified enough for an answer?
Yeah, unless I ask you to calculate the answer in decimal form or something. But anyway, I know you guys are desiring a surprise attack mission. And also, this surprise attack mission comes with strings attached. The strings that are attached to it are, we don't meet tomorrow, so you just have this. All right? Sound good? Yes, so I'll collect this Wednesday.
You don't have classes?
We do not. I will not hold class tomorrow because you have this work to do.